Good morning everyone, how's it going? Dr. Bennett here. I just wanted to give you a few hints and tips about this truss analysis for lab 7. So here is a diagram of the truss, and the first thing to mention, as you will recall from Professor Zwick's videos, is that we essentially have fixed supports at these 4 points, A, B, C and D, right? Now, if you cast your minds back probably over 2 years for most of you now to ES 201 statics, right? You'll recall that if you're analysing a truss in 2D, like we're going to do here, the most unknowns that you can solve for is 3, because you can only apply 3 equilibrium equations in 2D, right? Sum of the forces in X, sum of the forces in Y, and the sum of the moments about some point. So the first thing we need to do is make some assumptions about these supports, or change the type of supports, in order to get this system down to a statically determinate system. Because as it stands, we have a statically indeterminate system, because we potentially have 3, 6, 9, 12 unknown reaction forces due to the fixed supports as it stands. So what you might want to do is consider changing these supports down here, B and D as I've drawn it, to one pin and one roller support, for example, because a pin would have 2 reaction forces and a roller would have 1 reaction force, right? And then leave A and C free, right? So there's no real unique way of solving this system. You just have to make appropriate choices of your supports and justify why you've chosen them, right? So that's the first thing. So if you see in my example here, what I've done is I've chosen a pin support at point B, therefore I have these 2 reaction forces in the X and Y directions. And I've chosen to use a roller support at D, just so that my truss is supported, and that I'm left with at most 3 unknown reactions to solve. And I've left the top part of the truss free, right? And that then gives me a statically determinate system, because I have 3 unknowns and I can apply 3 equilibrium equations to this 2D system and hopefully solve for those unknown reactions. So the solution method for this will be, well, the first step is to apply the equilibrium equations, right, to find these unknown reactions, and then you will need to apply either the method of sections or the method of joints in order to find the axial forces in these 2 members here, which I've labelled lowercase a and lowercase b, where the load cells are of the truss, right? So for example, I could make a cut through the truss here and apply the method of sections to find the axial force in member A, and I could make a cut through here to apply the method of sections to find the axial force in member B, right? So that's the first step of the solution method, and hopefully by doing that you should get some numbers out that are somewhere in the ballpark, but we're not expecting your theoretical results of this truss analysis to be anything like close to the numbers that were coming out of the computer, right? Because the number of assumptions that we've had to make in order to solve this is going to lead us to some inaccuracies in our calculations. So be sure to mention all of those assumptions. So for example, the assumptions we've made in order to reduce the number of unknowns down with the supports, the assumptions that we've made about all of the joints being frictionless pin supports. In reality, they're not. See Professor Zwick's 4th video on the truss, where he discusses how these in reality are pinned together. Other things as well, like we've neglected the weight of the truss itself in the analysis. So be sure to discuss all of those things when presenting your results. As I say, we're not expecting your theoretical calculations to match the numbers coming from the computer, but as long as you justify what you've done in order to be able to solve it and explain some of the inconsistencies and how they arise, then you should be good. So I hope that helps out a little bit. I hope you're all keeping yourselves virus-free and keeping your heads up during this difficult time. So keep checking Canvas for updates, and we'll be with you shortly for lab number 8. Cheers.